All right, I said we are going to discuss the gas reactions further. That's what this section is about, equilibrium constants for reactions involving gases. Remember from Chem 103 that the concentration of a gas in a mixture is proportional to its partial pressure. And in gas reactions, it is often far more convenient to report pressures instead of concentrations. So we can give our equilibrium constant in terms of partial pressure. So our Kp is going to be the partial pressure of C raised to its coefficient times the partial pressure of D raised to its coefficient divided by the partial pressure of our reactants raised to their coefficients. When you're using Kp, it's important to use your partial pressures in atmospheres. Your values of Kp and Kc are not going to be the same. They are equal to each other when you're not changing the number of moles of a gas. But if you are, as happens in most reactions, you can convert between the two by taking your Kp is your Kc times the gas constant times the temperature raised to the power of delta N. The delta N is the moles of gas in the product minus the moles of gas in the reactant. And we will look at an example of that. So for the following, calculate Kp or Kc at 27 degrees Celsius. And remember, our Kp is equal to our Kc times RT to the delta N. So for this first reaction, we're given a Kc. And so our Kp is going to be that Kc value, 8 times 10 to the 25th, times R, 0.08206, times our temperature, 27 degrees Celsius, is 300 Kelvin. Our temperature always needs to be in Kelvin when we're dealing with gases here. And our delta N, we have 2 moles of gas on our product side. We have 3 on our reactant side. So 2 products minus 3 is -1. So we have to take our coefficient there is going to be -1. So our Kp is going to be 3.25 or 4 because we're down to 3 times 10 to the 24th. For our other reaction here, we're given a Kp value. And if we rearrange our equation, we can see that our Kc is going to be Kp divided by RT to the delta N. So our Kp here is 3 times 10 to the minus 17 divided by, again, that's an 8, sorry, times 300 because both reactions were at 27 degrees Celsius. Here we have 2 moles in our product. Again, 3 in our reactant, so that's going to be to the -1st again. 2 minus 3 is -1. So our Kc value here is 7 times 10 to the -16th. So there's that math worked out. All right, what is the equilibrium expression for the reaction below in terms of pressure, and how would you convert that Kp to a Kc? So why don't you pause the video, work that through, and then I will give the answer. So my Kp is my partial pressure of my N2O times my partial pressure of my nitrogen dioxide divided by my partial pressure of my nitrogen monoxide to the 3rd power. And then converting that Kp to a Kc, My Kc is going to be my Kp divided by RT. And then my delta N in this case, I have 2 moles of gas on my product, 3 on my reactant. So, like all of our examples so far, it's going to be to the negative first power. Okay, what's the equilibrium expression for this reaction? We're just going to walk through some examples here. And again, pause the video, make sure you know how to do this. We're going to be doing this for a long time. My Kp is going to be my partial pressure of my dinitrogen oxide squared times my partial pressure of my nitrogen dioxide squared divided by my partial pressure of my nitrogen monoxide to the 6th power. Okay, what happens when we have more than one phase? We talked about this rule that we don't use the phase that's different from everything else, but this will show kind of why. So if we have the reaction of carbon monoxide to make carbon dioxide plus solid carbon, it doesn't matter if we have a small pile of carbon or a large pile of carbon, as long as our concentrations of our gases, adding more carbon, solid carbon, isn't going to change the partial pressures of our gases. And so that solid phase does not show up in our equilibrium equation. There really isn't a good way to write the concentration of a solid anyway. You can say how many grams there are, but concentration as in moles per unit volume doesn't make sense for a solid. So we don't use it. So let's look at an example. Write the equilibrium expression for the reaction below. So we have 2 gas phases and 1 solid phase. So our Kp for our gases is going to be the partial pressure of our carbon monoxide to the 4th power divided by our partial pressure of our nickel complex here, NiCO4. Also in the gas phase, we don't use our solid phase in our equilibrium expression. All right. Multiple choice question here. What is the equilibrium constant for 2 hydrochloric acid plus 1/2 oxygen? It's in equilibrium with Cl2 plus H2O, chlorine plus water. Everything's in the gas phase. If the equilibrium constant for the reaction below, this Kp, is 0.0752. So really the question is, how do we get from the second equation back to the first one? So we're going to reverse the reaction and divide by 2. So if I reverse it, it's 1 over 0.0752, and dividing by 2 is going to take that to the 1/2 power. So my answer is 3.65. So there we go. For the following reaction, 2 nitrogen dioxide is in equilibrium with dinitrogen tetroxide, and we are given these partial pressures. What is the Kp? So we know our Kp is going to be that 1 over the partial pressure of NO2 squared. We're given our Kp, or our partial pressures. So we can plug them in and solve it, and we get an answer of 56.1.